No, let me join with my tablet. This is lecture 4. Which lecture is it? Yeah. Just a small recap. Last class we saw uh, the chain rule for entropy, which is h of x1 to xn, can be split using the chain rule and condition of the entropies as h of xi given xi minus 1 to x1 summed over all I is equal to 1 to n. Then we saw mutual information conditioned for a random variable z. I of xy given z is h of x given z minus h of x given y and z, which can also be written as the expected value of log of p of xy given z by p of x given z times p of y given z. Then we saw the chain rule for information. I of x1 to xn semicolon y is the summation of I of xi colon y given xi minus 1 to x1. Then we saw the formula for the conditional relative entropy d of p of y given x parallel q of y given x. This is the relative entropy of the conditional PMFs averaged over all values of x. So averaging over x, p of y given x log of p of y given x by q of y given x. Or it can also be written as expected value of log of p of y given x by q of y given x, where the expectation is over the joint distribution p of x comma y. And using this, we can write the chain rule for relative entropy. The relative entropy d of p of x comma y parallel q of x comma y can be written as the relative entropy of the marginal distributions plus the relative entropy between the conditional distributions. This is something we saw by the second half of last lecture. Today, so this is recap. Today we'll be looking at a few inequalities. First is the Jensen's inequality. Oh, I don't know if this was captured in the recording, but since it's a recap anyway, it's fine, I guess. I'll just show it once. Okay, today what we'll cover is Jensen's inequality, information inequality, some consequences of Jensen's inequality, and logsum inequality. So first, let's start out with Jensen's inequality. And for to state Jensen's inequality, first we need a few definitions. The first definition is the definition for a convex function. For a function f of x is said to be convex, and convexity is over an interval a comma b if for all x1 x2 in the interval, for any 2 points in the interval, and for any number lambda which is between 0 and 1, including 0 and 1, the value of f evaluated at the point lambda x1 plus 1 minus lambda x2 is less than or equal to lambda f of x1 plus 1 minus lambda f of x2. So such a function is called a convex function, but that's also a bit ambiguous because if you want to be more clear, you say that it is convex down because if you're looking from below, it looks like a convex. So this convex and concave are similar to what you see in lenses. So this function is convex down and concave up. That means when you're looking from the top, you see a concave shape. When you're looking from the bottom, it looks like a convex shape. Hello, hello, are you there? Yeah, so my laptop crashed and my internet went out at the same time. Yes, it's working now. So I don't know about the internet, but I recently had I told you, right, I had given my laptop for repair. So I changed the battery. Sometimes some weird stuff happens now. Hopefully nothing else happens. Okay. Convex function, you know, right? Okay. Yeah. Yeah, it should lie within the line. Yeah. Um, for convex function also, you have to. It depends on the function. There's no general proving technique for this type of thing. For some function, yeah, strictly convex if the equality holds only if lambda equals 0 or lambda equals 1. That is only at the endpoints. The function will look something like this. This is f of x, is the y-axis, x is the x-axis, and suppose it's convex in this interval. Then you pick 2 points, x1 and x2, and you pick some number lambda between 0 and 1. Then lambda x1 plus 1 minus lambda x2 will be some point in between x1 and x2. So this will be lambda x1 plus 1 minus lambda x2. If you pick lambda equals 0, that will be equal to x1. If you pick lambda equals 1, that will be no. If you pick lambda equals 1, it will be x1. If you pick lambda equals 0, it will be x2. For any other lambda, it will be some point in between. Then if you evaluate the function at that point, then the function value will lie below this chord connecting the. So this point at x1, this has value f of x1, and at x2 it has value f of x2. So this point will be lambda f of x1 plus 1 minus lambda f of x2. And the function evaluated at lambda x1 plus 1 minus lambda x2 will always be below the line joining f of x1 and f of x2. So below that chord. That is, any chord you draw will always be above the function line itself. So then it is called a convex function. Then we will define a concave function as follows. A function f is concave if minus f is convex. So examples of these would be, so for convex function, The examples would be parabola. F of x is ax squared plus bx plus c, where a greater than 0, and f of x is equal to ax squared plus bx plus c if a less than 0 would be concave. Another example for a convex function is uh, f of x equals c power x. And for a concave function, you could have f of x is equal to log x for all x greater than 0. The linear function f of x is equal to ax plus b is both concave and convex. The function f of x equals x cube is convex for positive values of x or non-negative values of x and concave for negative values. So that's why we talk about concavity and convexity in an interval instead of so some functions might be convex in only a particular interval, a concave in one particular interval, and they can be linear, both concave and convex in some parts. So the interval is important. Now, given a convex function, we have the following. So a way to find out whether a function is convex is from calculus. Uh, if the function f has a second derivative that is non-negative, alternatively it can be positive over an interval, the function is, I'll write fn instead of function, it's convex, alternatively it's strictly convex over that interval. And the proof for this is we use the Taylor series expansion for functions around a point x0 in the interval of convexity, around some interval, let's say. It's a point in the interval in which the function is convex. Then we can write it as f of x0 plus f dash of x0, x minus x0, plus etc. You can expand it to, you can keep on expanding, but if you want to truncate it to a particular point, then it's possible. So this f of x will be exactly equal to f of x0 plus f prime of x0 into x minus x0 plus f double prime of x star x minus x0 whole square by 2 for some point x star that lies between x0 and x. So uh, the Taylor series expansion, it will be exact if you keep expanding, you keep taking the derivative and keep on expanding. So it's an infinite series, but you can replace uh, the tail end of that series with the term that is of a 1 degree smaller. So that is, if you want to replace all the terms after the third derivative, then you can replace it by evaluating the second derivative at some point. This this result is from calculus, so you'll have to go and see in a calculus course. I won't give a proof for that result, but using this now we have that f double prime is a positive quantity, or at least a non-negative quantity from the hypothesis of this theorem. So since f double prime is greater than or equal to 0 for all x, it's also greater than or equal to 0 for x star, and we have x minus x0 whole square for real numbers, it's greater than or equal to 0. So the third term is always a positive term. That means f of x is greater than or equal to, if we drop the third term, f of x will be greater than or equal to the sum of the first two terms. So now what we do is we take x0 to be equal to lambda x1 plus 1 minus lambda x2, and we evaluate the function at x1 and x2. So if we evaluate it at x1, what you get is f of x1 greater than or equal to f of x0 plus f prime of x0 into x1 minus x0, which is x1 minus lambda x1 minus 1 minus lambda x2. If we evaluate it at x2, we get f of x2 greater than or equal to f of x0 plus f prime of x0 into x2 minus lambda x1 minus 1 minus lambda x2. So here you can write the two terms as 1 minus lambda x1. Then you can take the 1 minus lambda common to write that as 1 minus lambda times x1 minus x2. Similarly, here you can write it as lambda times x2 minus x1, because this x2 will multiply with this x1 and will get cancelled out with this x2, and you will be left with lambda x2 minus lambda x1, which is lambda times x2 minus x1. That is, f of x1 is greater than or equal to f of x0 plus f dash of x0 into 1 minus lambda times x1 minus x2, and f of x2 is greater than or equal to f of x0 plus f dash of x0 times lambda times x2 minus x1. Now we multiply the first equation by 1 minus lambda and second equation by lambda. Both are positive quantities, so the inequality won't change, inequality direction won't change, and then we add. So you will be left with lambda times f of x1 on the left hand side plus 1 minus, sorry, you multiply the first equation by lambda and the second by 1 minus lambda. So you'll get lambda times f of x1 plus 1 minus lambda times f of x2 is greater than equal to lambda times f of x0 plus 1 minus lambda times f of x0, which will, the lambda term will cancel out. So you'll be left with just f of x0, f of x0 plus you have f prime of x0 into 1 minus lambda into lambda times x1 minus x2, the first inequality. In the second inequality, you have the same thing with x2 minus x1. So those two terms will also cancel out. So you'll be left with only lambda f of x1 plus 1 minus lambda f of x2 is greater than or equal to f of x0, where x0 is uh, lambda x1 plus 1 minus lambda x2. So if f double prime of x is greater than or equal to 0, then the third term in the Taylor series expansion will be a positive term. So the function value is greater than or equal to the sum of the first two terms in the Taylor expansion, and that we can manipulate to get lambda f of x1 plus 1 minus lambda f of x2 is greater than or equal to f of lambda x1 plus 1 minus lambda x2, which means that it is a convex function. So that proves the theorem that if the function has a non-negative second derivative, then the function is convex. So that's a way to find out whether the function is. But for this, the function must be differentiable in the first place. F of uh, f of x and f prime of x both should exist, and f double prime should also exist. So it should be kind of a smooth function. Now, once we know what a convex function is, we can use that and state the Jensen's inequality. The theorem, we call it Jensen's inequality, which states if f is a convex function and capital X is a random variable and script X, uh, that is the set of all values that capital X can take, must be in the domain of the function, is in the domain of f. Then you can write expected value of f of x is greater than or equal to f of expected value of x. So that's the inequality. Yes. Uh, a concave function we have defined as a function for which minus f is convex. So minus, you can use the inequality for minus f, then it will become expected value of minus f of x is greater than or equal to minus f of expected value of x. And expectation is linear, so you can take out the minus sign and write it as minus e of f of x greater than or equal to minus f of e of x. and you can flip the multiply by -1 on both sides, and the inequality will flip. And moreover, huh, yeah, yes, that's exactly what it means. Only for a convex function. Yeah. So this expectation value is similar to taking is exactly taking the sum of the value weighted by some factors that are greater than or equal to 0, less than or equal to 1. So you could think of this as extending the definition of the convex function for larger number of values. So say here you have this definition of a convex function for two values, right? X1 and x2. And uh, for some value lambda greater than or equal to 0, less than or equal to 1, then you could think of this as a probability distribution for the two values x1 and x2. Say you could say that there is some random variable x which can take values from script x, which is x1 and x2. It's a binary random variable. That is, it cannot only take two values. And the probability of the first value is lambda, and probability that it will take the second value is 1 minus lambda. Then lambda x1 plus 1 minus lambda x2 is the expected value of x. And lambda f of x1 plus 1 minus lambda f of x2 is the expected value of f of x, right? So expected value of x is by definition x times probability of x. So I'm saying if you take x to be a random variable that can take the values x1 and x2, and the probability distribution is lambda 1 minus lambda. Because lambda is some quantity between 0 and 1, and the sum of lambda and 1 minus lambda is 1. So you could say that if there were only two values that had a probability distribution lambda and 1 minus lambda, so if the random variable takes value x1 with probability lambda and x2 with probability 1 minus lambda, then the function is convex. Yeah, from the definition of the convex function, it's the same as the Jensen's inequality. So the Jensen's inequality, you could take it as a generalization of what it means to be a convex function. So this is only defined over 2 points, x1 and x2. Jensen's inequality is defined over n points. So it says expected value of f of x, but when there are more points, right? The probability distribution of this f of x uh, will be different in the sense that there can be multiple. random variable values that go to the same function value. So x could be 1, 2, 3, 4, 5, 6. F of x could be all the odd numbers go to 0, and all the even numbers go to 1. So in that sense, the probability distribution of x and the probability distribution of f of x are different. 1 minute. So the expected value of f of x, in the end, it will still, it's just a subtle point there. It's a small difference from the 2 point example. Because in the 2 point example, the yeah, there also both the random variables can go to the same value, same function value. So I don't know where I was going with that. Anyway, that's the Jensen's inequality, and the equality condition will hold. So moreover, if f is strictly convex, then the equality in the above inequality implies x is equal to e of x with probability 1. That is, that x is a constant. Okay, that is Jensen's inequality. The proof for this, I don't think I'll be covering the proof for this. So you can check the textbook for the proof. Thomas and Cover page number. I don't know the page number, but it's in the first chapter. There's a subsection. No, it's in the second chapter. There's a subsection uh, for Jensen's inequality, and I think they have proved it. But I won't be proving it here. So it's mostly uh, trying to use induction, right? Um, the convex function definition, as I said earlier, it's it's the case of Jensen's inequality for only two different values, you could say, and it would be kind of easy to verify by using the definition of convexity and the expectation value. And then once you prove it for only 2 points, then you can use induction and prove it for more points. So the proof you can check any textbook for proof. Okay. The We'll move on to the next inequality, which is information inequality. We'll state it as a theorem, the information inequality. So given this is just a statement that I think I had mentioned it in a previous lecture, but I didn't prove it there. So given two probability distributions P of x and Q of x for some random variable x that takes values from script x, the relative entropy is a non-negative quantity. That's what the information inequality states. With equality, so in most of the inequalities in information theory, we'll also give conditions for when the inequality will be satisfied with equality. So when it will become equal. In this case, it will be equal only if the distribution of p of x and q of x is the same. That is, they're the same distribution. I will give a proof for this inequality. We'll start out with uh, giving a letter to denote the support of the probability mass function p of x. It is A is a set of all x such that p of x is greater than 0. So we exclude all those points whose probability of occurrence is 0 according to the distribution p. That is called the support of p of x. The support can be defined generally for any function, any non-negative function. You can say the support of that function is a set of all points where the function is not equal to 0. Then, so just for convenience, we will take the negative of the relative entropy d of p parallel to q. That will be equal to minus x belong to script x p of x log p of x over q of x. Now I'll do two things here. Since p of x is equal to 0 for all the values not in the support, and it is not equal to 0 only for the values in the support, so I can sum over only the points in the support, sum over x in A, and I can take the negative sign and bring it into the log, so it becomes p of x log q of x over p of x. Now, earlier I had shown you a graph, right? Log function, this log is a concave function. So, uh, since it's a concave function, we can, like you said, for a concave function, the Jensen's inequality is flipped. So, expected value of f of x is less than or equal to f of expected value of x, right? So, this looks like expected value of f of x, where the function f is log of q of x by p of x, and probability distribution is given by p of x. So then the expected value is summation p of x log of q of x over p of x. So I'll write it to the side here. This is a concave function. So e of f of x is less than or equal to f of e of x. So I can now say this is less than or equal to log of expected value of q of x over p of x. That is log of sum of p of x times q of x over p of x. This is, I'll call that 1, and this is by Jensen's inequality. Now p of x, since we are summing only over the support, p of x is not 0 in any of these terms. So the p of x will get cancelled out. You will be left with summation of q of x, x belongs to a. So I'll write this is equal to, and when I say that, the equal to does not apply to the first term, it applies to the previous term. So this is equal to, that's what it means. So this would be equal to log of sum of q of x, x in the support. So log is an increasing function. That means that if you sum, if this quantity is larger, then the log of that quantity will be larger. So log of sum of q of x, x belongs to script a, will be less than or equal to log of sum of q of x, x in script x. But if you sum over script x, you will get log 1, which is 0. I'll call this inequality 2. And this is because log is an increasing function. So from that we started out minus d of p parallel q. We got this is less than or equal to 0, which implies d of p parallel q is greater than or equal to 0. We have proved the inequality. Next we have to prove the uh, point at which the values at which it takes equality. So when both of them achieve, when d of p parallel q is equal to 0. So there are two parts here, one and two, where we have two different inequalities. So from these, in the second inequality, where we summed over all values script x instead of over all values of a, we attain equality if and only if a is the support of q. So for these two things to be equal, these log of summation qx x over a and log of summation q of x x over script x, uh, that would mean that for all values not in a, q of x should be equal to 0. That's kind of straightforward. Otherwise, if there was some value that did not belong to a but had a positive probability, then this sum would be greater than this sum. So since both sums are equal, then for all x not in A, q of x must be equal to 0. That means both p of x and q of x have the same support. In the first inequality, we attain equality if and only if, what is the condition necessary for the first inequality? So Jensen's inequality. So log is a strictly convex function, then x must be equal to expected value of x. That is, x is a constant. So the Jensen's inequality is attains equality only if x is a constant. And here when we use Jensen's inequality, the random variable x was actually q of x over p of x. So this is expected value of log of x, where x is q of x over p of x and expected value of f of x, and f is equal to log. So to get equality in this place, we need q of x over p of x is equal to constant. So q of x is cp of x for all x in a. But if we sum over all x in a, since that is the support of q of x, you get that is equal to 1, equal to c times sum over all x in a, which is again equal to c times 1. That means c is equal to 1. Therefore, q of x is equal to p of x for all x in a. For all x not in a, both are equal to 0. So q of x is equal to p of x if and only if, sorry, so equality if and only if q of x is equal to p of x for all x in a. And that proves the information inequality. That is, the relative entropy is always a non-negative quantity. Any doubt in this? Okay. Now, earlier we had defined the mutual information as a type of relative entropy. So, since relative entropy is positive, from this theorem we have a corollary non-negative non-negativity of mutual information. So, for any two random variables x and y, I of xy is a non-negative quantity, and with equality, if and only if x and y are independent. Hello? Yeah, we had seen that by the definition of h, I of x colon y, which is h of x minus h of x given y. So from that we can see that equality, it will be equal to 0 only if h of x is equal to h of x given y, which means that x is independent of y. But to show that it is always a, since we are subtracting h of x given y from h of x, to show it is greater than or equal to 0, you will have to show that h of x given y is always less than or equal to h of x. And you could follow a similar procedure as what we did for Jensen's inequality. You could use that, but directly we can write the proof, since we already have the proof for relative entropy. I of x semicolon y was defined as the relative entropy between p of x comma y and p of x p of y, which is greater than or equal to 0 with equality if and only if the distribution p of x comma y is equal to p of x times p of y. That is, x and y are independent. So there's one small point that this Thomas and Cover doesn't go into. I don't know if that John Massey notes goes into, but one of my professors, when he was teaching, so when we write this p of x comma y relative to p of x p of y, we should first be sure that p of x p of y is actually a probability distribution in the first place. So these are p of x is the marginal distribution of p of x comma y, and p of y is a marginal distribution of p of x comma y. So when we take the product of those, does it actually end up being a probability distribution? That's one thing to note. We are assuming that it does. We are assuming that p of x times p of y is in itself a probability distribution, but we didn't really show it anywhere. Okay, we'll take that for granted in this course. But in one of yeah, one of my professors had actually uh, worked around it in some other way. And another corollary is similarly for d of p of y given x parallel q of y given x is greater than or equal to 0 with equality if and only if P of y given x is equal to Q of y given x for all xy such that P of x greater than 0. So again, here it's slightly different because d of P of y given x parallel Q of y given x is not defined that is defined in a slightly different way. So P of y given x and Q of y given x, we don't take, they're not just distributions. We don't take the relative entropy between those distributions. We also average it over P of x. That was it in the recap. So this averaging is also there. So when we are showing equality and all, this thing will also come into place. That's why P of y given x should be equal to Q of y given x only for values such that P of x is greater than 0. If P of x is equal to 0 for some terms, those terms won't appear anyway. So we don't have that requirement that P of y given x should be equal to Q of y given x at those places. So this extra condition is there. And another corollary, you can extend it to a condition to mutual information and say that that's also greater than or equal to 0 with the equality if and only if x and y are conditionally independent given z. So even in this case, the when you do conditioning, it's a slightly different quantity. It's not as straightforward as I of x y. So the conditioning will change things up a bit. Uh, and here we are only taking discrete values. When we do this, all these things will kind of hold with slight modifications in some of the places for continuous random variables also. So when you're doing for continuous random variables, when you're trying to prove all these things, then there'll be slight changes and some of the supports and all, you'll have to be more careful. So I'm not going into those final details here. Yeah, no. No, I didn't get it. We can't, no, we can't say they are intuitive. You will have to actually write out the proof. Yeah, yeah, we can't do that in mathematics. It's x and y given z. No, but what a given z means is very mathematically precisely defined. I am just saying it as given z, but that's not a definition, no? What does it mean to say information between x and y given z? What does given z mean in the first place? Yeah, it is very intuitive. That's why it's nice when the results match our intuition, but that can't be taken as a proof. That's why I am writing these corollaries so that you can, these corollaries are true. I have not written the proofs, but people have proven these things. So now you can directly use them. And now you can say that, okay, from this corollary, I'm using it. But the smaller points, the subtle points. So, for example, this previous example, the conditional entropy with P of x greater than 0. So, this condition is not there for uh, normal relative entropy, right? For normal relative entropy, you just need P of x is equal to Q of x for all x. That's all. But when you have conditioning, when you have two random variables like this x and y, then it is sufficient if P of y given x is equal to Q of y given x only at points where P of x is not 0. That additional condition is there. That conditional condition doesn't come directly from the information inequality. Yeah. So just small points like this. Of course, it's very intuitive, and the proof itself is not won't take too many steps. Just extra one or two steps. Uh, Most of the time, you can use any of these terms anywhere you want. You see, there's no hard and fast rule for what a corollary or lemma theorem any of these are. There's just a general sense. People different. It's just personal preference, and some sense of it is lemma is usually some important result that you use to prove a theorem. Right? Before proving a theorem, you will prove a smaller, some related result that you will be. For example, before proving uh, Jensen's inequality, you should first know what a convex function is, right? And before proving this information inequality, you needed to know Jensen's inequality. So I could have called Jensen's inequality a lemma, and then I could have used the Jensen's inequality lemma to prove information inequality theorem. So usually lemma is something that you use to prove a theorem, but there are many cases where the lemma is much more important than the theorem itself, and it's a much more useful result. So that's one guideline. Second guideline is for corollaries. These are simpler results that follow from a theorem. So you prove a big theorem, and then uh, for slight modifications or slight changes you do to the theorem, and you can get some other result, some other related result. Then you call it a corollary. Yeah, because like you said, we proved that information is non-negative and relative entropy is non-negative, right? Then just conditioning on them, we intuitively would think that it shouldn't matter. So in that case, you don't have to prove it from scratch. You can just do smaller manipulations. Uh, for example, uh, with the data processing conditioning, just a small change because you are averaging over p of x, right? But the rest of the part, you don't have to prove it again. Yeah. So this only a small change is present. Only this part is changed. So, and to prove that part, there are not many steps. It follows directly from two or three steps from the information inequality. So that you would call a corollary. But there's no hard and fast rule. These are guidelines. And conjecture also is same. Conjecture usually is something that you think is true, but you don't really have a proof for it yet. That type of thing you can call it a conjecture. But then once you give it a proof, it will still if I still call it a conjecture, then once you have a proof, you'll usually call it a theorem from that point. Yeah, conjecture is like a guess that you haven't proven yet. Hypothesis is also like a conjecture in some instances. And in some instances, it's some assumption that you make to prove a theorem. So a hypothesis would be some assumption or a guess, similar to a conjecture. Yeah, but there's no set rules that anybody has given on what to call. So many, if you read different textbooks on the same topic, what is given as a lemma in something might be a theorem in something else. Or what is a theorem in one thing might be a corollary in something else. It usually happens in research papers. In textbooks, at least, it's more streamlined because people spend a lot of time, and the people writing newer textbooks would usually have read the older ones. But in research papers, nobody cares. Some different research groups are working on different things, so they can call it whatever they want. Nobody usually cares. Okay, next we'll move to another theorem that makes use of the above information inequality. And this theorem says the entropy of a random variable is less than or equal to log of the cardinality of the alphabet, where cardinality of script text is the number of elements in the range of x. And this will be equal, the equality hold if and only if the random variable x has a uniform distribution. So when I read that it's a script X, that's what it's called. Uh, there will be different fonts, right? So to denote different quantities, but there. So this script X is the range of all values that you can take. It's the alphabet, and X is the name of the uh, variable, you could say, name of the function, something like that. So you have a sample space that's denoted by capital Omega, which is the set of all values that a random experiment can take. And each of the outcomes here is denoted by little omega, right? That's the usual notation in probability, omega I. or some omega. Then this random variable x is a function of omega. So for each outcome, you will give another function. So if there is a coin, or if you roll a dice, the set of all outcomes omega is this, then you denote an individual outcome by small omega. They can take six values. The random variable is a function of those values. Let's say my random variable is takes the value 0 if it's an even number, it takes the value 1 if the outcome is an odd number. So x of 1, since 1 is an odd number, it will be 1. X of 2 is 0. X of 3 is 1, 0, 1, 0. So the set 0, 1 is the alphabet, or the range of x. So that's the set script x. That's clear, no? All right. To prove this, here you're saying for any random distribution, you're comparing any random distribution for a random variable x with the uniform distribution. So first let's give a name for the uniform distribution. We'll say like p of x, q of x. We'll say for uniform distribution, we'll say it's u of x, and u of x will have a constant value 1 over cardinality of x for all values in the script. So that is called a uniform distribution or a uniform PMF over script x. So if in the previous example for the rolling of a die, script x was equal to 0 or 1, and in a uniform distribution, um, this will have priority half and this will have priority half. So that is all odd numbers. The outcome will be an odd number with an equal probability as the outcome being an even number. So we will denote by the uniform PMF by u of x. Let p of x be any random PMF, be the PMF of x. Then we'll take the relative entropy between p and u, d of p relative to u, which is the quantity summation p of x log of p of x over u of x, x in script x, which is nothing but p of x log p of x minus summation p of x log 1 over u of x. Or you could take the minus sign inside and write this as plus p of x log u of x. This is nothing but minus h of x. This, since u of x is a constant quantity which is equal to 1 over cardinality of x. Sorry, I think this should be log of 1 over u of x with the positive sign. So 1 over u of x is nothing but cardinality of x. So this is cardinality of script x. And that is a constant quantity. So you can take that out and this will become summation over all x, p of x, and this quantity will go to 1. That sum is equal to 1. And there is a log here, I forgot. So this is log of cardinality of script x minus h of x. No, log was already there. So this is summation p of x log cardinality of x, right? Because u of x is one of, yeah, yeah, it's a constant value. Because the number of terms in script x is fixed. So this if this is equal to n, this is the p of x log n, and the summation is over all values of x. So this is a constant. You take that outside. You take that write that as log n times summation of p of x. So this becomes log cardinality of x minus h of x, and from the information inequality, this is greater than or equal to 0. And rearranging the terms, you will get h of x less than or equal to log of cardinality of x. With equality, if and only if uh, this distribution p of x is equal to u of x. So the shortest average description length h of x will always be less than or equal to, since it's less than or equal to log of cardinality of x, it will also be less than or equal to log of ceiling of cardinality of x. Ceiling is next is the integer that is the smallest integer that is greater than that particular value. Yeah, not smaller than x. Um, so since it's and with that many number of bits, you could express it directly, right? With using a block code. If you have one bit, you can represent a log of one, which is 0. You can't represent any information. Okay, sorry. If you have 2 bits, then you can represent them using log 2, which is equal to two different values. Then you can represent using log 2 base 2 bits. It is 1 bit, right? There are only two values. If there are four values, you can represent with 2 bits. So if there are cardinality of x values, you can represent with a log of cardinality of x bits. That log is actually over 2 base 2. So here what we are saying is, if you simply take uh, all if you simply find out the number of values that x can take, and you find out the number of bits you will need to represent those by using a code that assigns the same number of bits to all the values, then you'll get some type of code. The entropy will always be less than or equal to that number of bits. So what it means is you can't do worse than just simple block coding. So let's say you want to represent two different values, x1 and x2, and how can you do that? Yeah, with one bit can take 0 or 1, and you can assign x1 is 0, x2 is 1. What will you do if there are three values? No, you can do it with 2 bits. Yeah, you'll have 0001, 1011 with 2 bits, four different combinations. But you have only three of them, right? So you can't. You need 2 bits. There's no 1.5 bit or something like that. So with 1 bit you can represent two values. With 2 bits you can represent up to four values. So for three values also you have to use 2 bits. So when you take log of 3, it will be somewhere between 1 and 2. So when you take the ceiling of log 3, it will be equal to 2. So this is a block code because there is one block of bits that you use to represent each of the information symbols. So this is one block, right? If you have 4 bits, it's if you have 8 bits, it's 1 byte, right? So a byte is a group of 8 bits. So it's one block. So the no, I call it a block because you take the output is just a block of bits, and you do coding. So what happens is, suppose you want to transmit a stream of bits, stream of values, instead of transmitting a single value. You are transmitting x1, x2 up to xn, and you keep on going. You want to transmit this. So then, like in one of the earlier classes, you had asked, right? So if you want to transmit the a novel or something, then instead of representing each of the letters by some code word, why don't we represent the words in that novel by code words? You would ask the question like that. So that type of thing is actually done in other situations where uh, instead of assigning a code word for just one bit, one value like this, you take a block of bits, a block of values, right? So then what happens is, if it's a block of two values, say, if x1 can take any n values and x2 can take n values from some script x, then the block x1, x2 can take n square values, right? So for these n square values, each of them you assign one code word. Then whenever you get information, you split whatever you are getting into blocks like this. And you say uh, you get some code word, you receive this. You say that was actually representing a block of bits like this. So the input, so There's a channel over which you're trying to do communication. Before sending it to a channel, you will encode your data, and after receiving it, you will decode it, right? To encode it, what you do is you get a block of information bits. You take a, a particular number of information bits at a time. So you wait until you get those many bits. If someone is giving you, if before this there's some circuit that is giving you values, you wait until you accumulate four values. Okay. Once you have four values, then you encode that into say something like 8 bits. Then you transmit that over the channel. Here you will get some 8 bits with some error. And then the decoder will give you an estimate of what the initial 4 bits that were this x1 that you sent was, what the value sent was. So here in each stage, you are doing a coding over a block of information bits, and the code words is also a block. Right? So that type of stuff is called a block coding. Instead of doing this, another method that most people usually use in transmission in many application in communication, in your when you're getting this call right now, I'm talking to you, this does not do block encoding. What this does is uh, this previous circuit will keep sending values x1, x2, x3. It will, so instead of accumulating values like this and then transmitting, for each value it gets, there will be some buffers. There will be some storage units like this in this decoder, in this encoder. So it will keep storing those values x1, x2, x3, x4. Let's say it has stored already now at this point. Then it will calculate a function of these 4 bits. Right? It will do some manipulation with these bits. Then it will also send 1 bit. Right? When another value comes here, it pushes all these bits one place to the next and discards the last bit. Now there are new bits here. Only thing is, three of them are already used once. So next to x3, there's a new bit. It will do that same function, whatever it did here, and it will send 1 bit. So in this way, for each bit you are giving in, it will send out a bit. So it doesn't need to, initially it needs to wait, but once it gets started, you're not waiting for a block of bits. For each bit that is coming into the encoder, you're transmitting 1 bit. Same way, the decoder will give you a bit, and that you will decode. So that is so here you are not doing any block encoding, right? You are not doing coding and decoding over blocks. So that type of coding and decoding is it doesn't fall under block coding. Did you understand, or is there any clarification you want? Yeah, we'll see. We'll see block coding later also. Yeah, so you'll wait for a particular number of bits, then you will collect them into a block, and for that particular block, there will be a code word which you will transmit. And in the receiver, he receives that code word. From that, he can decode what block of information bits you sent. So it's done block by block. Yes, but there are error correction methods for that. So you can tolerate up to a particular number of errors. That will depend on the channel and how you have designed. So that entire thing comes under error correction. So that is also that we won't study under information theory. For that, you'll have to take an error correcting course. I think someone is already teaching, so you'll have to find someplace else. NPTEL has some lectures, I think. Yeah. So you can do error correction on blocks. Similarly, instead of blocks, you can also transmit in a stream. Forgot what it is called, but codes like that are uh, something called turbo codes, and turbo codes are used. So those are codes where you don't wait for a block of information and you don't transmit code words in block format. You just keep getting bits. Of course, you store some of them in a buffer, but you also keep for each bit that is coming in, you send out one bit, and then the decoder will be able to figure out. So in that sense, what I mean to say here is that um, so even in a block codes, right? Uh, there you could have variable length block codes. That is, you can allow for your information blocks to be of different sizes. So all and you can allow for your code words to also be of different sizes. It's just that once you fix the code words and information words, then everything is fixed. You don't change it anymore. So in that case, you can have variable length blocks. That is for different information vectors, you can have different length code words. So what I am saying here is that instead of having variable length blocks, if you have constant length blocks, then you will need log of cardinality x number of bits to represent that. Otherwise, in the previous example, right, for three different values x1, x2, x3, if you use equivalent blocks, then you need 2 bits, right? You need 2 bits 0, 0, 0, 1, 1, 0, you can say, and 1, 1 is wasted. If you are allowed to do variable length, then you can give 0 to x1 and 1, 0 to x2, 1, 1 to x3. So in this case, uh, whenever you send x1, you are actually saving 1 bit, right? When you send, if you want to send x2, x3, then you don't get any savings. But if you send x1, you are actually getting savings. So if x1 occurs with a good probability, then you are getting a good amount of savings on average when you send a long stream of bits. Yeah, 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 yeah. So that's a prefix-free encoding. That's what it's called. Yes, that's why I had told in one of the previous classes, right? We don't. Sometimes it might be better to do something theoretically, but practically we don't end up doing it. We look at the gains. So if by doing variable length coding we can actually gain a lot, then Yeah, that also is a contributing factor, the decoding and encoding complexity. That's what it's called. So information theory doesn't care about that, but practical systems you will have to care about in this decoding and encoding complexity. That's why even in your computer storage, right? Everything is stored in bits, bytes, words, x64, that this so 64-bit operations. So why do you need to do 64-bit operations to add 0 and 1? No point, right? To store also to store 0, one bit is enough. But to store one, just 0 and 1 and 2 and 3, very few bits are enough. Why would you need? But still, they give so many bytes worth of memory. Whenever at least 1 byte or 2 bytes will be there. Yes, but still, it's still in terms of bytes and words. But they don't do in some random number of bits, right? It can't be just whatever is enough. I will use that. That's not how it is. Some bits will be wasted. Uh, so that is only for practical convenience. How will you actually differentiate? How will you read and write? All those things will become much more complicated. That's the thing with information theory. A lot of the times, it is only good to give you a framework for which you can work in and give you something to achieve, right? It can give you an ideal, but in the end, the practically you will have to um, consider other things while trying to achieve that idea. Which field are you in? No, I just asked because not I just asked that. So, which field are you working in? Which field are you studying? Hmm. Yes, yes, yes. So, but I am teaching this course from ECE perspective. So, Kolmogorov complexity I won't cover. Yeah, for that you'll have to read from the textbook. Yeah, Cover and Thomas, I don't know which chapter. They said that in one chapter it is there. We'll have to find out which chapter it is. In one chapter, they have said that they explore the relation with Kolmogorov complexity and information theory. Um, yeah, so I don't know about the research papers in computer science, what they expect, but in these information theory related conferences and journals, right? They always look for proofs and asymptotic proofs. That kind of, they don't care about the practicality at all. So they won't ask you if you write a paper and you say this is the result that I got. These are the improvements that I have over previous things. This is a tighter bound that I have given, and this achieves the bound. And then they'll be pretty happy. They won't ask if there anybody going to use this or will anybody be even be able to use this. But if you go to a different type of conference like a communication WCNC or a TCOM or something like that, though in those situations, uh, when you submit a paper, they will ask, "What's the use of this?" So yeah, you could have a lot of results, a lot of bounds and all, but then in the end they'll say, "What will I do with the bound? How useful it is actually?" So that's the difference. Yeah. Okay. How much is left? So there's still quite a bit left. I'll end today's class at this point then. I uploaded that in the PM, what is it called? Moodle. That website is there, no? I shared links for the, I embedded, I shared embedded links for the lecture videos. I've actually uploaded them on YouTube, but the links I've embedded on that website. Along with that, the lecture notes are also there. Morning is difficult. I can shift it to some other day. Then you let me know when you are free. Yeah, yeah. You see if between next Wednesday and Saturday, if you have any free slot in the evening or night. If you don't have, then we can skip Wednesday's class and do it next Saturday. Okay. I have asked the. I sent a mail to the IES ISSS people to ask if this course can be extended for a few more weeks. Uh, we'll see when they reply. If they say it can't be done, then I'll just have to offer another course after this ends in January sometime to cover the rest of the material. Yeah. Anyway, if it goes to another course that will have next semester, then I can include that Kolmogorov chapter also. But I will have to read that myself first. If it doesn't go to that, then I'll probably extend it by another month and finish it. Okay, I'll see you next whenever you are free. Oh, this lecture actually went to 2 hours because of all the technical problems. I hope you don't mind. All right. Bye. I'll see you. You just send me a mail. You have my email ID. Good night. Good night.